Second. All right, we're on a 10-second delay here, so I'm going to have to make sure that this works. I've got tone now, at least, though. Okay, there we go. All right, so it's working. Sorry about that. Anyway, remember that we are live on Piazza for answering questions, and of course we've got the chat open on YouTube if you want to join that. Where we left off last week for error handling, I gave a really quick demo of a few utility functions, or I think that they were, what were they? Converting time, so given a total number of seconds, convert that to hours, minutes, and seconds. And then given sorry, this is the wrong one. Let me open up the right one. Let's see, let's go over here to the utils. There's a header file, there's the C file, and then there's the tester file that we wrote. And we wrote a convert time, again, that took a total number of seconds and split that out into a total number of hours, minutes, and seconds. And then a get total seconds, which was just the opposite. Right? Yeah, I think that this is what we did. I'm not sure, but in any case, it doesn't really matter because what we did was, because we were returning these things, returning them again by using pass by reference variables. In other words, pointers. That freed up the return value here to communicate an error code, a potential error code. So, for example, if the hours were null, right? If these were null pointers, we could protect against that by returning a null pointer error, or too low error, or something like that, right? We did this, right? I think we did, right? I think so. Okay. In any case, just to remind ourselves the general strategy here, it was defensive programming, right? You look before you leap. You look and see, am I about to divide by 0? Or am I about to dereference a null pointer? And then you don't do it. You back up and you say, well, if I did that, then I would end up having an error condition, maybe even crashing the program or something like that. So I'm not going to do that. Instead, I'm going to stop and return back to the calling function with a non-zero error code. Remember, error codes, by convention, 0 is associated with no error. Non-zero positive values are associated with a certain type of error. So you could say there's an error of type 1, there's an error of type 2, there's an error of type 3. But we don't want to have to remember those things, right? We don't want to have to remember that 1 was associated with null pointers, 2 was associated with a different type of error, etc. Instead, we want to use human-readable flag variables for that, or flag values for that. And to do that, we're going to have to introduce enumerated types, which we'll talk about here in a second. Remember, common mistakes are you do not echo an error message in a function. You can do that in a main, but that's the only place that it's appropriate to do that. You don't want to clutter up the output where most likely a human is not actually even there looking at the output. Again, 99.9% of all software is written to interface with other software, not for human consumption. You do not generally make errors inside of a function fatal. In other words, you don't call the exit function in the event of any error, right? You want to return back to the calling function and give them the freedom, whoever is calling this function, give them the freedom to decide what happens, right? Do they use a default value? Do they make it fatal? Do they go a completely different route? Whatever the choice is, it's on them to make that choice. You're just communicating an error code back to the calling function. Okay. All right. So let's continue from there. Before we get into the particulars of how enumerated types work, I did want to mention how C. Let me give myself some more room here, so that it always comes up to the, there we go. How C does system level error handling. Right? Now this is just going to be a demonstration. It's not necessarily something that you're going to use directly or indirectly, unless you're actually going to start doing some system programming, some POSIX compliant system programming. The POSIX standard actually only defines 3 error codes. Right? So So first of all, what is POSIX? I always forget. I think it's Portable Operating System IX. I forget what it stands for. So let's go ahead and look it up. POSIX. Right? Is the Portable Operating System Interface. There we go. So we're going to add an X at the end to make it sound cooler. Right? And so that's what POSIX is. Basically, it's another standard on top. It's not a C standard. It's an operating system standard. Linux is POSIX compliant. Unix is POSIX compliant. The Mac operating system is POSIX compliant because it's BSD based, etc. Usually the only operating system that is not POSIX compliant is, guess, Windows, exactly. So it is not a portable operating system interface that has everything that a POSIX compliant system would typically have. Now that might be different. I don't know, find Windows, right? POSIX for Microsoft Windows. So yep, Windows is not POSIX compliant. Instead, you'd have to put on something on top of that like Sigwin or MinGW or something like that. That might be changing, I don't know. But anyway, POSIX compliant standards actually define system level error codes. There are 3 of them that are in the standard. EDOM, E-range, and another one very, very seldom used, EIL-SEQ. EQ, there we go. So EDOM indicates an error in the domain. That's why it's domain of a function call, right? For example, we'll come back to this in a second. An E-range indicates an error in the range of a function call, right? So another example, what? Before we do this, let's understand what a domain and a range is. So think back to basic high school math. If you've got a function, what is the domain and what is the range? What is the domain? The x value, in other words, the set of all inputs. What is the range? The y value, or the set of all outputs. In other words, i.e. the domain, i.e. the input, there was an error with the input. E-range, well, that's the output. There's an error with the output, right, of a function call. So now, to understand this, let's actually look at a particular example of each one of these. For example, SQRT, if I call this on a negative value, right, is that defined? Is that well defined as an input to the square root function? No. So this would result in an EDOM error, okay? E-range, another example here would be log, base E, doesn't matter, of 0. So in math, if you were to graph the log function, what would it be at 0? No? Undefined. Well, if you took the limit and approached 0 from above, what would it look like? Let's go to Wolfram Alpha. And a natural log, of course, of x. What does it look like? At 0, it goes off to negative infinity. Well, is negative infinity a value in the range of representable values? No. So we end up with an E-range error, okay? EIL-SEQ is short for illegal byte sequence, all right? Rarely seen. In fact, it's so rarely seen that in my demonstration that I'm about to show you, I'm not able to cause one intentionally, right? So each one of these is defined in a header file called error no, right? Sorry, only 2 R's. And this is for error number, right? NO, the number, right? If in the event of one of these errors, a global variable called ERRNO, so the same thing, is set with one of those 3 possible values, right? What possible values are there? Well, first of all, there's 0, the convention that if there was no error, you called square root on 4, you got back 2. There's nothing wrong with 4, there's nothing wrong with that input, there's nothing wrong with the output 2, so there's no error. And this variable right here has a value of 0, indicating no error. All right? So what happens if you call square root on -1? Well, this variable right here is set to some value. Do we know what that value is? It 1? Is it 2? Is it 3? I have no idea. Do I care? No, because edom is a more human-readable version of that. Now, arguably, it should have been error in the domain of the function. That's too long. Maybe error domain or e, and then they of course then shorten it too much to edom. E-range, E-ran. I don't know I don't know why they they shortened this up really short. They didn't shorten this up really short, but it is what it is, right? So what are those numbers? I have no idea, and I don't care because I have those all caps terms that I can use in my program instead. Let's take a look at an example here. So I've created several variables here. A is -1, B is 2, C is 0, and I've got X. And we can see here, I'm going to run this program here in a second. Let's walk through it first, though. I'm going to call square root on B, in other words, 2. There's no problem with that. The square root of 2 is what? 1.41 blah, 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 blah. And so what value will error nose be set to? Note here that I am including that header file. That should be set to 0, indicating no error. Now I'm going to call square root on A, which is -1. That should result in an edom error. Now I'm going to print it out as an integer. It might be 1, it might be 2, I have no idea. It doesn't really matter, right? Does it? Because I can use this human readable form, edom, in my program. Was the error of type edom? Or was the error of type E-range? Or was the error of type illegal byte sequence? Otherwise, it was some other error, or maybe it was not an error at all, right? Then I'm going to go ahead and, actually I'm using something else here. There's a way to translate this error into, this error number into an error message, a human readable message. It's not going to be that, that helpful though, all right? But we will see what it looks like. And then down here, I'm calling log on 0, resulting in an E-range error, just as I said as in the example. And then I translate that into a human readable message. So let's actually see this in action here. I'll compile it. Oops. I need the math library. I'm on CSE right now, by the way, which is a Posix compliant system because it's a SUSE Linux operating system. Let's go ahead and run it. And we see that, well, the square root of 2 is 1.41 or 4 blah, 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 blah. It doesn't matter. The error was 0. Right? Now, calling square root on -1 results in not a number, negative not a number, and an error code of 33. I had no idea that that was 33. Right? I would actually have to look at the source code to see that it was the 33rd listed value, or that it had a number 33 associated with it. Then we call the error message, by the way, it was an edom error, numerical argument out of domain. Right? So there was an error in the domain. Otherwise, when we call log of 0, we get -inf, remember, log of 0, it's going to go all the way down to -infinity, and an error code of 34, which is associated with an E-range error. The numerical result is out of range. Okay? Now, what other types of errors are there? Only these three, or these two, and then illegal byte sequence are defined by the standard. But there are actually dozens and dozens of others. Let's take a look at just a Google search here for errorno.h source. There we go. We can actually look at the source file of a typical errorno header file, as long as it comes up. There we go. So there's an operation not permitted, eperm. There's an noent, no such file or directory. ESRCH, which is no such process. I don't know why SRCH is associated with a process, but whatever. If we go down here to 33, we see math software library stuff. edom and E-range. Those are associated with 33 and 34. But remember that there are dozens of these things. Right? There are dozens of these error codes that have been defined. If you're doing system level programming and you need to remember these all in your head, it's never going to work, right? So you're always going back to, okay, well, what was enomem or cannot allocate memory? Oh, that was 12, right? Don't use those. Remember what we called those? They're called magic numbers. Why? Where did they come from? Where are they going? What are they associated with? I have no idea. But at least this is a little bit more readable over here, right? No mem, right? No memory, right? So it's much better to use human readable flag values for these kinds of things instead of magic numbers, okay? To do that ourselves, we could, by the way, how did they do them here? They did them with preprocessor directives. Define eperm. The preprocessor will go through all the source code, and anytime that it sees eperm, it'll do a copy replace with 1, right? So they end up becoming magic numbers. You can do that. You can do it that way if you want. But another way of doing it is through enumerated types like we did last week, okay? So enumerated types. And it's not just error codes. It's anything that is fundamentally a list, right? So many pieces of data have a fixed and limited number of possible values, right? For example, right, the days of the week, months, right, or error codes, right? How many days of the week are there? 7, and they ain't making any more. How many months are there? 12, and they ain't making any more, right? These are lists of things, right? So in C, what you can do, in C, you can define an enumerated type to hold human readable terms for your list of possible values. Right? Here's an example. Let's do it for days of the week. So what we do is we use type def, first of all. Type def is short for type definition. Now, there are lots of built-in types already. For example, int is a built-in type. Double is a built-in type. Char, those are all built-in types, types of variables. What we're about to do is we're about to define our own variable type. So type def, type definition. And what type is it? It's an enum, or an enumerated type. Right? Enum is just simply short for enumeration. Now, what is an enumeration? It's a list. A, B, C, D. This is a list. Now, how do you usually write out a list? As a bullet-pointed list, right? This is the first item, second item, third item, fourth item. And you put it in 1 per line. And so that's what we're going to do, too. What's the first day of the week? Monday? Okay. Sunday. So many people would say Sunday. Some people would say Monday. Order is important. We'll go ahead and go with Sunday, though. Right? If you really want to go with Monday, we have very few votes here, so who wants to start with Sunday? 1, 2. Oh, yeah, so now you change your vote. Okay. Say what? Yes, I love democracy. And prequel memes, right? Tuesday. What else? Wednesday. I always have to sound it out like that to spell it correct. Thursday. All right. Friday. What are our days named for, by the way? Well, Sunday and Monday, those are pretty self-explanatory. Sunday, the sun. Monday, Moon's Day, right? Tuesday is the Roman god Tyre, I believe. Maybe it's Tyre, whatever it is. Tyr, Norse. Okay, Norse. And in that same vein, Wednesday is Odin's Day, Thor's Day, Freya's Day, and Saturn's Day, right? Saturn, which is not Norse, right? Saturday, did I spell it right? Okay, good. And then finally, we give our type a name. And for this, I'm going to use upper camel casing, day of week, followed by a semicolon, because this is a declaration. I'm declaring that there's an enumerated type. Here are the possible values: Sunday, Monday, Tuesday, Wednesday, Thursday, Friday, Saturday. Now, this is similar to the Oxford comma. It is optional, but you can also put it in. Right? So I tend to put it in there just to be consistent about it. If you ever do need to come in and add an 8th day of the week, I don't know, Leif Erikson Day, okay, Leaf Day, right? Then we'll go ahead and put that in there as well, right? But for now, we'll stick with the traditional 7 days in the week. All right. Now, note here the conventions that I'm using. Right. Conventions. Or I'll say observations. Right. Generally, we'll use upper underscore casing for list items. Right. We will use upper camel casing, excuse me, for enumerated type, the names of the enumerated type. Also, 1 per line. These are just style elements. Of course, you can go ahead and put them all in one line. It doesn't look very good though, right? It doesn't look like that nice bullet pointed list anymore. So I like to put them on one per line, just so that you don't lose the forest for the trees. Okay? Those are the conventions. Later on in your program, right? ... You can use them. See, I can say day of week, spelling it correctly. Today is equal to, well, what is today? It's Moon's Day, so Monday. All right, there we go. I can set today to be Monday. Day of week, next lecture. I can say that that is Wednesday, right, etc. All right, so other notes. Generally, you use, of course, type def enum to define it. Then provide a comma delimited list of items inside curly brackets. That was the syntax. Those are required syntaxes, right? You have to have an opening curly bracket, a closing curly bracket here. And then a semicolon at the end. Semicolon at the end of a declaration. Okay? Why upper camel cased on day of the week? That's just a convention to offset them. These are basically constants. In fact, we'll talk about how this is actually working in C in a second here. But they're used for constants. So upper underscore casing, like we did in the demonstration last week, where we declared it right here, up here. No error. So if you've got multiple words, you separate those words with an underscore, right? And that's just the convention. That's the modern convention. In fact, it's the old school convention as well, because they do it here, although they don't use the underscoring. But they do use E in front of all these to shorthand for error. Okay. Just to separate them from variable names and type names. Okay. All right. Generally, also, you declare enumerated types inside a header file, like I did last week, because you'll want to use them over here in this source file and use them over here in this source file and that source file. Well, if you put them in a different source file, then you end up having to use that source file, which is not how you do things. Instead, you always include a header file, so you end up declaring them in your header file. Of course, again, you can always use an alternative here and use a bunch of preprocessor directives if you really want to. Okay, but I take this opportunity to introduce enumerated types, which have more uses. You can do days of the week, you can do months, you can do anything that generally you have a small set of fixed values. It can only be these 5 things. Well, go ahead and list those 5 things out so that you can use the English human readable formats for those things. All right. All right. How does this actually work? Unfortunately, there really is no. This is kind of a hackish way that C did it. Internally, C assigns integer values to each element in the list, starting with, by default, 0. So, i.e., in the example above, Sunday has a value 0. Monday has a value 1, etc. Well, the last day of the week is, according to our convention here, Saturday. What value does it have? has a value 6. Just get used to 0 indexing because we're going to be looking at arrays next. And in computer science and programming, everything begins with a 0, including the first element in an array. Right? And we'll understand why probably on Wednesday or maybe next week. Consequently, you can really screw things up. So here's an example. Day of week. When? And I won't use I can't use a question mark here. Is equal to Monday plus Tuesday. Right? That's kind of weird. Have you ever wondered what happens when you add Monday to a Tuesday? Or Tuesday to a Monday? Does it make any sense? No, because it's a particular point in time. You can't add a particular point in time plus another particular point in time and get a different particular point in time. But in this case, you can. Why? Because Monday has a value of 1. Tuesday, therefore, has a value of 2. So 1 plus 2 is 3. And what's the 4th day? Because, again, you start at 0. Sunday, Monday, Tuesday, Wednesday. Right? So it ends up being Wednesday, right? Which is weird, right? And in fact, you can screw it up even more. When plus 50, right? Or when is equal to. When is equal to when plus 50. What value does that now have? 53. Do you see 53 things up here in the list? No. It's gone beyond the list, and it doesn't wrap back around. You could wrap it back around by modding out by the number of elements in the list, but I mean, it doesn't make much sense anyway when you start treating them like integers. But what you can do, so the takeaway here is understand that enumerated types are integers, but do not treat them like integers. Right? Don't go adding them. Don't go subtracting them or multiplying them together. It doesn't make any sense. All right? But you can use them in expressions. For example, you can say, if today is Saturday, then finally, printf, we can play football. Right? Yeah. But maybe not safely, unfortunately. All right, so Saturday, but at least we can watch football. We could always watch safely from home and let other people take the risk, unfortunately. Right? So understand that the actual representation is a bunch of integers. Don't treat them like integers, though. Okay? All right. Any questions so far? Okay, none online. So again, what we did over here last time, now that we understand how this is actually working, you understand why I put no error first, because that's going to be associated with 0. So no error, that's going to be 0. Now you can reset this, by the way, using the following syntax. It'll start at 10. Now this one will have a value of 11. This one will have a value of 12, 13, right? It's not usual to do that, right? Especially if you want to associate no error with 0. So 0, 1, 2, 3. But I don't have to use those in my code anymore. Instead, I can use error code. And instead of returning an integer, I can return an error code now. Return an error code. Right? Now, at the end of the day, there's really no difference here because it's still an integer. But I can now use human-readable terms instead of these magic numbers. And by the way, if I go back and I rearrange or I add things, like, oh, I don't want my null pointer error to be 1, I'll go ahead and put it like that. I didn't have to change a single line of code anywhere else. All I have to do is add to my list or change my list and rearrange it all I want. Over here, if you did it this way, you definitely have to be careful because if you couldn't just take, say, edom and move it up 3 spots because something already has the value 30, right? But if you use an enumerated type, then yeah, great. There's also another reason to use enumerated types over preprocessor directives. It's because the compiler will actually keep track of these And so if you're debugging, you'll still be able to use these human readable terms in a debugger like GDB, which we'll be looking at in a couple of weeks. If you use if you use a preprocessor directives, nowhere it's not retained in your source code. All right. So there are a couple of arguments in favor of using enumerated types over preprocessor directives. All right. All right. Any questions so far? Yeah.
Since all those items have like an integer value, if you like returned 0, would it still have the same value?
Yep. If I go over here, if I return 0, but now I've got that really defeats the purpose of using enumerated types. So yes, you can treat them like integers, but you generally shouldn't. Right? Yeah.
Is there ever a purpose? Like, I know you said we would never use it, but like, would there ever be like a situation where we would set like no error equal to 10 and have the list start with 10?
I can't think of any other than if there's some particular reason that you want to. I mean, no, because even if you come back so the question for those online was, is there a reason that you would ever want to use that syntax of starting it at 10? The only thing that came to mind was you're saving those first 9 or 10 spots, 0 through 9, for something. But if you're using enumerated types anyway, you can always come back, shift everything down, and you didn't have to change any lines of your code anywhere else anyway. So I don't see why. Yeah, maybe there's a use case out there that I'm not familiar with. I don't know. Yeah, good question. If you find one, let me know. But otherwise, that pretty much ends the error handling module, which was module 6. And you'll note that the reading for this week that was due at 5 o'clock, it was rather short because error handling is pretty quick. It's pretty simple. You return an error code, and then in the calling function, you handle it however you want to handle it. Oh, that's a no error, so keep going. Or, oh, that's a too low error. Okay, well, I'll handle that one way. Or that's a null pointer error, so I'll handle it a different way. Right? It's a pretty simple concept, and so it's not. We don't dwell on it too much, and that's why your reading was short. And it's why your hack this week, and your lab for that matter, is simply you taking your stuff from last week and updating it to do some error handling, right? Okay. Let's go ahead and get rid of this. And that means that we can start on something much more substantial. I'll go ahead and close this. Save this so that you have it on the notes. Remember that we do post the notes on GitHub. I push them out every evening after I get home. And let me open up some new notes. So let's start talking about arrays. So it's really, really rare to only deal with one variable or one piece of data at a time. Right? Generally, you have entire collections of data. You usually want to process or operate on a collection of pieces of data. Right? In C, collections of similar pieces of data can be stored in arrays. Right? And what I mean by similar pieces of data is that you can have an array of integers. You can have an array of doubles. You can have an array of characters, which gets us into the next topic, well, the next topic, strings, after the midterm. But essentially, arrays are a collection of variables of the same type. In C, you cannot have an array. In some languages, you can have an array that holds what are called mixed types. So the first one would be an integer, the second one would be a double, the third one would be another integer, the fourth one would be a string or something like that. Those are mixed types. That's not allowed in C, right? Or at least it's not usual in C, right? They have to be the same type. You have an array of integers, or you have an array of all doubles, or whatever you have an array of. They have to all be the same type generally. Arrays have a single identifier, that is name, right? And elements in an array can be accessed using an index, right? The first element is always at index 0. The second is at index 1, etc. Right? Consequently, if there are n elements in an array, the last one is at index what? Let me change this to code mode. There. So, where's the last one? Index n? Careful, if there are 5 things in there, and it starts at 0, 0, 1, 2, 3, 4. So where's the last one? N minus 1. Right? Indexing is achieved, there we go, using square brackets. Right? So for example here, a sub 0 would be the first element. Right? Now we're going to start this discussion by looking at something called static arrays. Later on, we will only be using dynamic arrays, but we'll use static arrays initially to show you how to use these things and show you the syntax of using these things. Static arrays. Static arrays are arrays of a fixed size that are allocated on top of the program stack. So remember that program stack? A stack is a LIFO, last in, first out data structure. Your program loads up. Then the main is called. Then main calls another function. That function calls another function, calls another function. And you've got this stack of stack frames, this call stack, right? Well, a static array is located, if you create an array of size 10, of 10 integers, then they're all allocated in that program stack frame, okay? And we'll see a visualization of this later on. Here's the syntax. There we go. Let me give myself some more room here. There. So int ARR sub 10, right? What this does, and I need a semicolon, of course, will create an array that can hold 10 integers. And when I have this, now I've got an array called ARR that holds up to 10 integers. So I can also create an array that can hold, say, 20 doubles. How do I do that? Well, double numbers of 20. These numbers, when you declare an array and you put a number inside of square brackets, you are declaring its size. There are 20 elements in this array. There are 10 elements in this array, right? It's just like any other variable declaration. So observations. So just like any other uninitialized variables, the contents of an array have no default values. Right? So let's go ahead and take a look at what I mean here. Let's go ahead and touch demo.c. There we go. And I'm going to grab some code, just some boilerplate code over here. There. Close that. Oh, where am I? Oh, okay, fine. I'll open it up over here. There we go. Get rid of what I don't need. There. So let's go ahead and create an array of size, say, 10. An integer array. A sub 10. Right? Now what I'm going to do is I'm going to iterate over that array and show you what's already in there. For that, I'm just going to use a regular old for loop. For int I, starting at 0, I is less than 10, I plus plus. Why did I start at 0? Where is the first element in the array? A sub 0. Then the second one will be in a sub 1, a sub 2, a sub 3. Go up to, but not including the size of the array here, 10. Why? It'll go up to 9, which is the last element in the array. Right? And let's go ahead and print those out and see what's in there. A sub whatever, %d, is equal to %d end the line. And I'm going to print out I, showing you that, the index at which I'm printing, and then a sub I, the actual ith element in the array. Right? Now let's see what's in there. GCC demo. Usually they're going to be mostly zeros, but it's not always the case. And, oh, I'm glad that it's not the case here. What do you see in there as default values? Garbage, right? Random crap. Whatever was in the stack frame before it was allocated. Whatever was in that memory location that belongs to that stack frame, you've now created 10 integers in there, and whatever garbage was stored in that memory location before is now being tried to, it's trying to interpret that as an integer. Right? So there are no default values. You really have to be careful there. If you're expecting something to be in the array when you create it, like this, that's a wrong expectation. Right? There's just random garbage in there. Right? Generally, there is random garbage stored in uninitialized arrays, right? So once you have an array, though, you can start setting the values, right? Using indexing and the normal assignment operator. So let's go ahead and start setting values. Say ARR sub 0. Did I call it A? I called it A over here. I'll go ahead and stick with ARR because that's what I did over here. All right, ARR sub 0, I can set that equal to 42. ARR sub 1, I can set that equal to -5. It can take any integer value. I can set ARR sub 2 equal to 3.5. What's going to happen there? Truncation. It ends up getting the value 3. All right, truncation results in 3. Right? ARR sub 9 sets the last value. Give me your favorite integer. 42 again? Okay. All right. Sets the last value. Uh-oh. What if we do the following? ARR sub 10 is equal to 101. Or ARR sub -1 is equal to 102. Right. Uh-oh. What happens there? Say what?
It just can't do it? Or what is the error?
So remember, C is a language that if you want to shoot yourself in the foot, it's going to ask you what caliber you want. And it's not going to complain, right? But what is going to happen is, remember, this is allocated in memory. Here's my chunk of 10 integers. Where's -1? It's down here, right? That's a valid memory location. That's a memory location that likely belongs to me because it's so close in the stack frame. Up here, 10. That's just one off too. That memory location, maybe that does belong to me, but what do I end up what do I end up doing up here? I end up corrupting my own memory, corrupting the memory down here, corrupting the memory up here. Or even worse, I end up corrupting memory that doesn't belong to me. Let's try it. Actually, let's try these two things right here. ARR sub -1 is equal to 101. ARR sub 10 is equal to, is equal to 102, or 201, let's say. And thank you, A and A, because I used A over here. GCC, all right, run it. Stack smashing detection. I love that term. I didn't know that CS50 would do this. Stack smashing detection. What am I? So I've got my program stack, right? What am I doing? I'm smashing it. I'm smashing it with a hammer that I shouldn't be doing that. And so it aborted, right? You're not always going to have that issue. In fact, if I do this on something else, REPL, let me grab this entire program here, and let's try it over here. With a different compiler, a different operating system, you may get different results, right? It's perfectly fine. It's perfectly happy. Over here, the CS50 runtime environment is a little bit more sophisticated, apparently, because it can actually detect that I'm doing something wrong and say, whoa, stack smashing detection detected. So we'll abort that program. Over here, it's perfectly fine. You screwed up your own memory, so what, right? So you have to be really, really careful. You have to be good stewards of your own memory. Now, if I do something really, really, really illegal, I'll go ahead and get rid of these two things. A sub negative, or let's go with some very large number here. Not that large, but 100 million. There we go. Let's just go with 1 billion is equal to 42. That's probably way beyond my stack frames. Now I'm getting into memory that doesn't belong to me. And I'm probably going to get a different error message here. Let's find out. There, segmentation fault. A different error message because I'm no longer smashing my own stack. My stack ended, say, right here, and I went way beyond that, several megabytes, several hundred megabytes beyond that, into some other program's memory domain. into some other memory program's segment of memory. And so I'm faulting out on my segment of memory, and so I get a segmentation fault. Likewise, if I do that over here on REPL, I'm sure that I would get the same thing. Right. Try that again, segmentation fault. You're trying to access memory that doesn't belong to you. It's illegal. You can't do that. It aborts your program. Okay? All right. So, be careful. Don't do things like that. Right. Accessing elements outside of the array, of your array, accessing elements outside an array is undefined behavior. Right? It may be a segmentation fault. It may, and now I'm going to add something else to the notes here, be a, what was it called again? Stack smashing? It may be a stack smashing. What was it exactly, though? Oh, okay. It wasn't smashing the stack below. Now, but it was smashing the stack above. Oh, stack smashing event detection or whatever. It may be a stack smasher, smashing. It may simply corrupt your own memory, right? It may or may not result in bad consequences, but it is just not good, right? Don't do it, right? Make sure that you are good stewards of your memory and that you're not accessing memory beyond the bounds of your array. Convenient syntax? More syntax, I'll say. Right? You can declare and initialize a static array in one line. Declare, excuse me. Right. So for example, if I want the first 7 primes, int n is equal to 7, I'm just keeping track there of the size of the array. I can do something like this. Primes is equal to, well, what's the first prime? 2, 3. Give me some more primes. 5, 8, 9, 10, 11, 12, 13, and then 17. That's 7 of them, right? Note here, did I provide the size of the array? No. Compilers are dumb, computers are dumb, but at least they can count. The compiler will go through and see, oh, you've provided 7 integers there. So I can figure out that the size of the array that you want is 7, and it'll take care of that for me. You can put that in there, by the way, if you really, really want to, but why? Let the compiler do at least a little bit of thinking for you, right? Besides, if you ever come back and add an 8th prime, a 9th prime, then you have to go back and change the size of the array as well. So this is something called eliding or elision. What does elision mean in, say, grammar? Does anybody know? What's an example? Are you gonna go? Are you gonna go to the Husker game when's the first home game? I don't remember. Are you gonna go to the Husker game? I elided something there. Are you going to go? Right? I said, are you gonna go? I'm eliding several syllables in my speech in order to say something faster, in order to take out unnecessary details, unnecessary enunciation. Now, some people, especially non-native speakers, would say, no, that's necessary. I don't understand what the hell you're saying because it's non-standard English. But in programming languages, you can do the same thing. You can elide things away, E-L-I-D-E. You can get rid of them because the compiler can take care of them for you. Right? Note here that the syntax is curly bracket, semicolon. And it will assign each value. This is the prime sub 0. This is prime sub 1. The last one is prime sub 6. You can also change them later on if you really want to. Right? But I introduced this syntax for one reason. Right? In general, there is no way to determine the size of an array after it has been created in C. Right? You will see many, many, many bad tutorials tell you otherwise. Do not listen to those bad tutorials. Those bad tutorials are restricting their attention to static arrays and using some under the hood magic to get the effect of being able to determine the size of the array. They are not correct, right? They can succeed in very, very limited circumstances, but in general, there is no, let me repeat, there is no way in general to determine the size of an array after it's been created. As a consequence, in C, you must keep track of the size of an array, of every array that you create. Right? This is known as memory management, right? Or bookkeeping, right? Also called bookkeeping. Right? So bookkeeping is, like an accountant. All right, well, we've sent out 20 products, so we're owed this much money. We've bought this much product, so we owe this much money to other people. All that is kept down in one big giant accounting book, a ledger book, and updating. Okay, well, we received that payment, so check that off. We sent that payment, so check that off. Balancing your checkbook, that's bookkeeping, right? Balancing a ledger book, that's bookkeeping. Keeping track of the size of an array so that later on you may be able to clean it up, that's also bookkeeping, right? It is your responsibility. It is your responsibility to keep track of all the sizes of every array, right? As a consequence, if you ever pass an array to a function, you also need to pass the size of the array to the function, right? And the size of an array, can you have an array of 3.5 elements? No, that doesn't make much sense. Can you have a negatively sized array? No, that'd be weird, right? Here's an array. You can have an array of size 0, nothing in it. You can have an array of size 1. You can have an array of size 0. But can you have an array of size -1? How would that work? If you declared an array of size -5 megabytes, does that install new RAM into your computer? No, it doesn't make any sense. So in general, this is a separate integer value, right? That you pass in, right? So let's look at one final example today. Right? We've already done, let's do it over in the IDE, right? Declare an array of size 100, set each element equal to 1, 2, 3, etc., up to 100. Then sum up the numbers. Then print the elements in the array. Then sum up all the numbers. Sum up all the values. All right, there we go. All right, let's do that exercise as our last thing for the day. All right. I'm just going to come over here to this demo. Right. So, how do I create an array of size 100? Int. What should we call the array? It just represents numbers, so nums or numbers or nos or just a or array, right? Of size how big? 100. Right? Now, what's in that array right now? If I just printed these out, it would be garbage. Right? In fact, we already had that. So for int I equals 0, I is less than 100, I plus plus. Printf, a sub %d is equal to %d and the line, a or I and then a sub I. Right? I shouldn't have erased what we already did. Let's go ahead and see what's in there. Oops, not a, ARR. There we go. And let's run this again, and you'll see again, it's just garbage, garbage, garbage. So what is garbage plus garbage? Two garbage, that's good. Still garbage though, right? So what we need to do is we need to initialize this array first. For int I equals 0, I is less than 100, I plus plus. Right? I will set each element in there equal to 1, then 2, then 3, then 4. So is this going to achieve that? Let's find out. Clear. GCC, run it. The last one was 99 because the indexing goes up to 99. So if I want to start out at 1, what do I need to account for? I need to account for that 0. So is this correct? Should I add 1 to the index? No. Right. If I do that when I get down to the bottom, then I'll have, what was that called again? Stack smashing event, right? I like that. So I need to add the 1 over here. Okay. Could I have just done this? Plus equals 1. What's garbage plus 1? Still garbage. Right? So, I plus 1. There we go. Now let's go ahead and make sure that this works. Run it. And there. Now we've got 100 down to 99, blah, 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 all the way down to the original one, which is 1. Okay? Now let's go ahead and iterate over it again. For int I equals 0, I is less than 100, I plus plus. No, I was writing 100 a lot. Maybe let's take a step back here and improve this code a little bit. 100. What if I changed it over here from 100 to 1000? I would have to change this and this and this and this. Right? Whereas if I did proper bookkeeping, what could I do? Int n is equal to 100. And now all I have to do is use a variable, n, and n. Right? I'm going to sum them all up. So sum plus equals ARR sub I. That gives me the ith value in the array. And so I need to, of course, declare sum. There we go. And let's print it out. Printf, sum of values 1 through %d is %d. And the line. So I'm going to go up to n, including n. And the sum is sum. Does anybody know what the sum of the first 100 numbers is? No? Gauss did it when he was a kid. It's from Gauss's formula. And I think that story is apocryphal anyway. Let's go ahead and find out. Oops. What's a good way of, good job online. You already got it. But how did you find that out? You probably opened up Wolfram Alpha, sum of first 100 integers. Or you just remember that it was 50-50. All right? Or you remembered Gauss's formula, in which case, good on you. All right? So, do I get 50-50? Oh, Gauss must have been wrong. Wolfram Alpha's wrong. My code's perfect. My code's right. What was my mistake? What value does sum have on line 17? Garbage. So garbage plus 1 is still garbage. Garbage plus 2 is still garbage, etc. If I want to sum, where should I start? At 0. Yay, now I get 50-50. My code was, in fact, wrong. Right? I know it's hard to believe, but yeah. All right, so be it. And if I change this to 1,000 and this to 1,000, then what's the sum of the first 1,000 integers? I think it's going to be, oops, that's not what I wanted. 500, 500. Oops, over here. Let's run it again. All right, 500, 500. I'm starting to be convinced that this is correct. 100. What about 1 billion? What's the sum of the first 1 billion? 1, 2, 3, 1. There we go. So save that. Might take a little while. We'll find out. Ignore that. I was hoping that it would go for at least a little while. 1 billion. 1, 2, 3, 1. Wolfram Alpha knows. It's going to be 5 and then a bunch of zeros and then 5 and a bunch of zeros. Why didn't my program know? It didn't get an overflow because it would get an overflow because that's too big of a number for an integer. But in this case, I got a segmentation fault. How many this is 1 billion integers. Each integer takes how many bytes? Do you remember that from lab 2? 4 bytes, right? So 4 times 1 billion. 4 billion bytes. 2 I don't know, gigabytes? How many gigs is that? That's 4 gigabytes. Well, that's not that much in today's memory, but it's a hell of a lot more than I have in stack space. Stack space is generally limited to megabytes at most. In fact, 4 megabytes is the usual standard. What did I do? I said, create a stack frame with 4 billion integers in it. Right? Well, what's going to happen to my stack? It's going to get full, and then what happens when it's over full? It overflows, stack overflow. Right? You can't do that. So we have reached the limits of static arrays. We need some other solution. That other solution we're going to look at on Wednesday. Right? 1 billion integers, that's nothing. Any questions? Okay. Then I will see you on Wednesday. Have a good lab tomorrow.